Alrighty, good morning again, ladies and gentlemen. So with us today, we have Dr. Sanjay Campbell, not unfamiliar to any of you in the room because he is a graduate of the University of West Indies Mona campus. And it so happened that through interfacing with Professor Auclair, he attained a postdoctoral position at McGill University. And that would have been in February 2020. So he just made nearly the last flight that was going to head to Canada before this pandemic. So, I mean, of course, it wasn't the last flight. I think it's February, yeah? So if it was February, then it was a couple, would have been cutting it close-ish at some point in time because we all recall that we shut down in the middle of March. So this could have been a postdoc that didn't happen, is really in essence of what I'm saying. And so, as I said, we do know Dr. Campbell. He has had experience with teaching here on the UMona campus in terms of being a TA and doing summer programs, that type of a thing. And his work was in marine natural products chemistry. As you would have known, we did work together. Seemed like many moons ago, but yes. And so that is what I have to say as introductory words for Dr. Campbell. As I said, we all know him, and so his presentation, and I trust that in addition to what he's going to talk about, which is entitled, his talk is entitled "Approaches to Modulating Bacterial Response to Immune Attack." I would hope that you would have questions for him because in the past, up till now, we have had persons who have transitioned into the US and overseas for, maybe over 15, 20 years, Sanjay is just there for about a 2-year period. And so it's kind of closer to the graduate student type of an experience. And so we trust that, he'll be able to field questions from you that you may have in terms of what's it like transitioning to life in another country, that type of a thing, because I'm sure he has gained a lot of experience from his sojourn for the past couple of years. And, things must be very different in that different type of an environment from what it is that many of us are accustomed to here in Jamaica. So, with no further ado, I will hand over to Dr. Campbell, who's going to be sharing with us this morning. Go right ahead, Dr. Campbell.
Okay, thank you, Dr. Gallimore. All right, so as Dr. Gallimore has pointed out, my presentation is entitled Approaches to Modulating Bacterial Response to Immune Attack. So as it relates to the presentation for this morning, okay, we're not moving.
Go in presenter view and okay.
Okay. All right. So I'll briefly talk about normal immune response and the role of itaconic acid. I'll then talk about the degradation of itaconic acid by some pathogens and how inhibiting the degradation of itaconic acid is a good approach to treating, it's a potentially good approach to treating bacterial infections. And then I'll just briefly talk about the synthesis of these potential inhibitors and how we incorporated a biocatalytic approach. All right, so macrophages, when they're activated, also known as phagocytes, they form the primary line of defense against pathogens. So what happens is that the bacterium is going to be engulfed by the phagocyte, which forms a phagosome. Phagosome is going to connect with a lysosome, which form a phagolysosome. And when that happens, these cells, they're going to secrete various substances to achieve a bactericidal effect. And one substance that is secreted by macrophages is known as itaconic acid, which is a diacid. So it's a known antimicrobial compound, as well as it's known to inhibit the enzyme isosaccharic lyase. So isosaccharic lyase is a key enzyme of the glycosylate shunt, also known as the glycolytic cycle. So just to briefly talk about that. So the glycosylate shunt importance is that it's going to be allowing bacteria to bypass the oxidative steps of the tricarboxylic acid cycle. So therefore, it's conserving carbon atoms for gluconeogenesis, as well as there's an upregulation. There's upregulation when acetyl-CoA is a direct product of the pathway, as well as the glycosylate shunt allows the bacteria to use different carbon sources, such as acetate fatty acids and alkanes. So in essence, what I'm saying is that, it's essential for the survival it's essential for the survival of the bacteria within the macrophage. So beyond their carbon fixing role, isosaccharic lyase also malate synthase of the glycosylate shunt have been implicated in virulence, persistence, as well as antibiotic resistance. So just to reiterate the point, the glycosylate shunt is considered essential for the survival of pathogens in mammalian systems. And it's known, where if you're infected with bacteria, there's going to be overproduction of itaconate, and this is understood as a bacterial response of macrophages. So some bacteria or some pathogens, such as Salmonella, Mycobacterium, and Pseudomonas, they have evolved to degrade itaconic acid, also known as itaconate. So if they're degrading itaconic acid, that's going to allow for less sensitivity to itaconate, and this has implication for the infection. So if it's less sensitive, therefore clearing an infection will become harder or longer. And just to say the importance of these pathogens, Salmonella, it's a known foodborne pathogen, and it's a major health concern for public health. It's associated with 1.2 illnesses annually in the US, and approximately 100,000 infections are due to antibiotic-resistant Salmonella. Pseudomonas aeruginosa is an opportunistic pathogen, and it causes morbidity as well as mortality. It's a leading cause of morbidity and mortality, and in cystic fibrosis patients and immunocompromised individuals. So it has become clear that antibiotic resistance is a global health problem, and it's a significant hurdle that we need to tackle. So new ways and new strategies are needed. So now I'll just talk about how these bacteria go about degrading itaconic acid. So the degradation starts with ICT, which is known as itaconate coenzyme A transferase. So this allows the itaconate to be added to a CoA moiety, forming itaconyl CoA. The second enzyme, ICH, itaconyl CoA hydratase, is going to hydrate that double bond to form citramyl CoA, and the citramyl CoA is going to be cleaved by citramyl CoA lyase into pyruvate and acetyl CoA. So we're seeing where these pathogens are actually using the itaconic acid as food, as acetyl CoA can be incorporated in the glycosylate shunt, as I had mentioned previously. So if we could form a drug that could potentially inhibit any of these enzymes, then that would be a new way that we could potentially treat bacterial infections. So how do we go about forming these drugs? So to note is that the substrate of ICT, ICH, and CCl suggests that a CoA is recognized by all three enzymes, and that would suggest that perhaps forming CoA derivatives / analogs could work as degradation inhibitors. So we decided to focus more on ICH, which is the second enzyme of the pathway, as forming substrates or products could of substrate or products of CoA could potentially work as inhibitors. So we're trying to mimic these substrates are the products, and we decided to use a pro-drug approach because it's known where if we could synthesize this part of the molecule, we could feed it to the bacteria, and because of the CoA biosynthesis pathway, that would allow for the production of the actual CoA derivative. So just to talk about the CoA biosynthesis pathway, so in bacterium, the natural CoA biosynthesis pathway, it normally proceeds using 5 enzymes, starting with pantothenic acid. Alternatively, though, pantothene can be used to be transformed into CoA by the action of these 3 enzymes: pantothenate kinase, phosphopantothene adenyl transferase PPAT, and DPCK, which is D-phospho coenzyme A kinase. So in essence, we're harnessing the biosynthesis pathway to produce our CoA mimic that we're hoping can be used as an inhibitor. So something I should have pointed out earlier is that for the enzymes of the pathway, ICT, ICH, and CCl, there isn't any known crystal structures at the moment, which is why our approach is to try and mimic the substrate or the product. Also, to point out that this bond is very unstable, so our approach is to switch out with an amide bond, and that will allow for some stability. And if we have all 3 enzymes, PANK, PPAT, and DPCK, that will allow for the production of our mimic that we're hoping can be used as an inhibitor of any of the of ICH specifically. So there has been some success with this approach using a small molecule that we call 3NP. So our mimic is 3-nitropropanoic acid, and it has been transformed into the CoA derivative, and we believe that it is working against these enzymes. So how do we go about actually seeing that if it's working or not? So we set up a checkerboard assay. So a checkerboard assay is where we're varying 2 things at once. So before I talk about the checkerboard assay, I just want to give some context as to a bacteria that has the degradation pathway versus a bacteria that doesn't have the degradation pathway. So E. coli, it cannot degrade itaconic acid. And as I mentioned before, Salmonella contains the enzymes that can degrade itaconic acid. So if we should set up a assay where we're varying the concentration of itaconic acid, we're seeing where it's taking much more itaconic acid to kill the bacteria versus with E. coli, we're seeing where just under one is able to kill the bacteria. So this is just to show the contrast between itaconate containing bacteria versus E. coli, which doesn't contain the enzyme that can degrade. So to point out as well, this is done in nutrient-poor root medium. As I mentioned before, that's when the glyoxylate shunt is going to be activated. So we know for sure. So now, when we would feed the bacterium Salmonella with this compound that we call 3NP, we're seeing where, so now let me explain the checkerboard assay. So we're varying two things. We're varying the concentration of itaconic acid, and we're varying the concentration of 3NP or prodrug. And what we see where as we increase the concentration of the 3NP, we're seeing that there has been like a shift and less itaconic acid is needed to kill the bacteria. So in essence, we're seeing a resensitization effect. So this has produced, so this shows some proof that the concept works. So in terms of my specific work now, so we have this one compound, or this one hit rather. So we're basically exploring different motives and seeing if we can find other, or if we can create other inhibitors. So these are some of the compounds that I have synthesized. So the red portion, again, just to reiterate the point, it's the itaconic acid mimic. So what's the rationale? So for the nitrile mimics, the idea is that the presence of an electrophile functionality, that it's attacked by the catalytic cysteine thiolate in the active site of the enzyme, and that's if the enzyme is a covalent, if it's covalent inhibition. But most of my targets, it's bioisosteric replacement. So what do I mean by bioisosteric replacement? So these tetrazoles and thiophenols, as well as sulfonamides, are known to be bioisosteres of carboxylic acids. So
this information at the beginning. If you don't know the zip file, I think the tryptane or tryptation will be this that particular number assignment. It says 1112174 assigned submission file SS5. It says that your name is there.
Marcel, are you able to Dr. Porter, you're...
No, I'm not a host. I'm unable to mute him.
Dr. Porter. Dr. Porter.
Sorry.
Sorry about... Okay. Proceed, Sandy.
okay, yeah, and we're back. Sorry about that, guys. Right. So I was saying that tetrazoles, thiophenols, and sulfonamides, they are known bioisosteres of carboxylic acid. So a bioisostere is basically something that can mimic the functionality. So it's known that tetrazoles, sulfonamides, and thiophenols, they can mimic a carboxylic acid. All right, so I'll just briefly take you through the synthesis of one of these small molecules, the tetrazole. So the synthesis starts with pantothenic acid. So first we do a 1,3 diol protection to produce compound 2, which is the protected pantothenic acid. And then with DCC coupling, we're able to couple the diamine moiety to produce our pantothenate intermediate in 35 to 70% yield. So after that, it's to produce the itaconic mimic portion. So for that, I start with glutamic acid. So a oxidative decarboxylation using TCCA under basic conditions allow for the production of the 3-cyanopropanoic acid in 60% yield. Then I do a benzylation to protect that carboxylic acid to produce 1.82 in 60% yield. And then it's to do the cycloaddition using TMS N3 to produce the tetrazole in 70% yield, and then remove the benzylation protection group, and then need to protect this amine, and we do that with a trityl moiety. From there, it's to attach the 2 moieties, and that's done with DCC coupling, and then to deprotect using acetic acid wart-up mixture, and that would yield our compound. So to point out, I'm not the only person that's doing synthesis. There is also Dr. Kolia and Chungling that also produce different mimics so we have a large library of compounds that we want to test for inhibition. So from here, it would be to synthesize the CoA mimic derivatives, and again, to emphasize, would be basically feeding the small molecule. So if we can somehow purify these 3 enzymes, we can feed the molecule, and that will allow for the synthesis of a CoA derivative. So I have been able to express and purify these enzymes, and it's done with E. coli. So it's the E. coli, pancake, PPAT, and DPCK. So from here is to see if these compounds can actually be converted. So we have set up a screening assay using the first enzyme, pancake, because it's the limiting step. And because we have a lot of compounds in our library, we want to see like which compounds can actually be activated by the enzymes, can be transformed by the enzymes. So we have set up a screening to see like, okay, which one we can move ahead with. All right, so let me just talk about how we go about this assay. So the first enzyme, pantothenate kinase, is known to add a phosphor moiety, and it's ATP dependent. So the ADP that is produced, we can couple that with pyruvate kinase that we can buy, because that's commercially available, to produce pyruvate. And the pyruvate with NADH with LDH is able to produce lactate. And then that requires NADH, which is gonna be reduced. So therefore we can monitor the reduction of the NADH spectrophotometrically. So these are the components of the assay. So as I said before, we purify pancake. We have the pyruvate kinase, lactic dehydrogenase enzymes that we can obtain commercially. So we also set up our controls. So control pantothenic acid, which is a native substrate of the enzyme, or test compound, negative control, as well as a enzyme control and a negative control, no enzyme and no compound. So the assay is performed in triplicate and it's done at 30 degrees. So it's initiated by the addition of ATP. And as said before, we're monitoring the reduction or the consumption of NADH, and we can monitor that at 324 nanometers. So it's a kinetic assay. So it looks like this, where, as I said, we're seeing the reduction of the NADH. So therefore, that is evidence that the compound is being phosphorylated. So from there, we can take the initial rate and we can compare to see like what motif is being transformed at a faster rate. But what we're happy with is that all the compounds with the different motifs are being transformed. So therefore the pancake is promiscuous, and that's good. So there's a different motifs. So I've been screening. So I screened all the compounds that I synthesize, as well as Chongling and Rohit synthesize. And basically we're seeing transformation of pretty much different structural motifs. So that's good. So from there, it's to see if the other two enzymes can actually transform our compound. So for this, it requires HPLC traces. So I'll set up, so in setting up this assay, so start with pancake plus PPAT, and then all three enzymes, pancake, PPAT, and DPCK. And the reaction is initiated by the addition of our small molecule. So these are some HPLC traces. So this compound, so the HPLC trace with pancake only. So this is the compound, and then this would be the phosphorylated compound. And as we add the other enzyme, you realize that there is the appearance of this peak. So that would therefore mean that it has been transformed into the D-phospho-CoH3NP, and then we're seeing this peak. So this is just to show that the compounds can actually be transformed into the CoA analog. And I've also done that with this compound. So this is the phosphorylated, and with two enzymes, appearance of this peak, and then with three enzymes, we're seeing where these two peaks are decreased, and then the appearance of this peak. Also did it with this compound. Again, we're seeing the product. So we're seeing where it actually works. So now the task is to move to preparative HPLC purification of these mimics, and then we can go ahead and do our inhibition studies once we have the enzymes of the degradation pathway, which is ICT, ICH, and CCL. Then we can go about doing some inhibition studies, as well as continue with our whole cell model assay. So that's where we're at now. So as it relates to the project or other persons on this project, there is struggling that I mentioned before, and Dr. Kalia. We also have graduate students, David and Dustin is one of our past students. In terms of the biology side of things, that's Jacob and Katerina, which is an undergrad. So there's also different projects that we perform in our lab. So there is a project, mechano-enzymatic degradation of polymers. So basically it's to degrade plastic or chitin or cellulose in moist conditions. And on that project, we have Jane, Sandra is a past student, and Dr. Selma, Mario, and Dan. There's also the pantothenamide project. So on that project, there is Shay, Annika, past student, and Victoria. And there is also a P450 enzyme, allosteric cooperativity, and that's Alexa and Samuel on that project. So just want to acknowledge Professor Karine Auclair and in terms of grant from the CIHR institution. So again, Auclair Lab, you can follow us on Twitter. And thank you. And we're having a warm spring. It's a whopping 2 degrees. And I'll be happy to take any questions.
A whopping 2 degrees. Imagine that. Imagine that. Okay, thank you so much, Dr. Campbell. And at this time, I will go ahead and see if there are any questions from your former compatriots here this morning, as well as any of course, our fellow lecturers. Are there?
Sir, I have a question, Dr. Gallimore. Sanjay, thank you for, sorry, Dr. Campbell. Thank you for the presentation. Could you go back to the synthesis of your compounds, particularly the triazole? Okay, couldn't you use a different reagent to do this? The triazole synthesis, particularly probably something like sodium azide. Could it not achieve the same formation, or why is it why did you specifically use a TMS?
That is an excellent question, Mario. I actually tried
Marcel.
with the sodium azide, but it didn't work.
Oh, because in my experience, I've used sodium azide and it can produce this type of compound as well. This type
Right,
of,
yeah.
so I was just wondering. Okay.
Yeah, for some reason the reaction didn't work. I speculate the energetics of it.
Did you heat it or was it done at room temperature?
So
Because
it has to be heated. I was doing it at like 120 degrees, but still no product.
all right, so the reason I asked because the mechanism that the paper I was looking at, where it was nothing, the structures weren't similar to yours, of course, but they typically heat it to remove the nitrogen gas so it won't form that product. So I'm wondering if maybe if you tried it at a lower temperature, if it would work. But that is just something I was just wondering.
Okay.
Well,
Okay, I can try it at a lower temperature.
I can send you the paper. I think there's
Sure, yeah.
reason for the heating. All right, thanks, Dr. Campbell.
Thank you so much, Marcel. Even looking on the slide, I see the yield of that last product at 2.57 is significantly lower than many of the other processes. Do you have any thoughts in terms of what happened there in terms of that significantly lower yield, which seems like a fairly simple process?
I'm losing some of my product because trityl chloride can also attack the carboxylic acid group.
Okay.
So that's also a thing. However, when I try to do the reaction without without unprotected,
You protect.
yeah, the yield is also low. So that tricky synthesis.
Okay. All right, no problem. Are there any other questions for Dr. Campbell related to the chemistry or other things? I noticed that you have quite a few from looking at that the last couple of slides. You have quite a few undergrad students in the lab. Can you give me an idea of what the population of what the student population is like, and you know, how has COVID impacted even the undergraduate students working in the lab space?
Okay, well, the population of students, I'm not sure. I only started seeing students recently because everything was online. And then that also affect undergrads being in the lab as well. So it's just like usually undergrads are in the lab for the summer or throughout the semester, depending on what program they're on. So it's a common thing. But yeah, because of COVID and everything, there wasn't that much. But yeah, for now, we're having undergrads.
Okay, so your undergrad students didn't come in for labs any at all? All the labs were virtually conducted, as far as you know. I know you're not in the student space per se, but you're saying you're just seeing students now?
Right. Yeah. The labs were virtual, and then like it depends on what year you're in. So like if you're like a final year student, then because the classes are more smaller, then they would probably accommodate you. But yeah, but where it's virtual, they try to put everything virtual. And then for now, I know it's like a hybrid situation where you either have the option to go to class on Zoom, or you can actually come in. So, but we still have to wear masks and everything. So yeah.
Okay. No problem. Any other questions, ladies and gentlemen? Any other questions for Dr. Campbell? And look in the participant listing because I'm not seeing everybody. Oh, Professor Reese, go ahead.
Right. Thank you, Dr. Campbell, for your talk. My question just had to do with the enzyme isolation. I mean, from what I heard, you use E. coli, which overexpresses the enzymes. But I know you're speaking to a chemistry audience, but I was just wondering, yeah, you showed your page profiles and all of that, but I just wondered if you could take me through how you actually got the enzyme. I guess you grew the organism in some medium, but I was just wondering how you isolated it.
Yeah, sure. So first we have to transform. So we have the vector. Let me just ensure I don't miss a step. Right, so the first thing that I would have to do is to get the gene inside of the plasmid of the bacterial. And in our case, we're using E. coli. So once the plasmid is in, so that's known as a transformation step. Once that is in, then it will be to grow on a plate to get colonies. From there, it's to inoculate with a larger culture. And then from the larger culture, we're gonna grow overnight, usually. Well, I'm missing a step. So we have to induce for the overproduction of that specific enzyme. Once we have induced for the overproduction, then there is to grow. And then from growing, then it's to get the cells. So we usually get the cells by centrifugation. After centrifugation of getting the cells, then comes the part, so that's cell harvesting. That part is known as cell harvesting. So after cell harvesting is to lyse the cells, and we do that with a specific buffer. So after lysing the cells with a specific buffer, and separating the other cell debris, it's to do chromatography. And in our case, we're doing affinity chromatography. So the protein of interest, it's tagged with a histine tag, and therefore the protein of interest is gonna be bounded to the column, and then everything else will pass through. And then we can unbound with a specific concentration of the buffer. And then from there it's to what's the word I'm looking for? To filter and to remove the buffer. And then we need to ensure that the enzyme is active, and right here we need to show that we actually got the enzyme of interest. So just to talk about this slide, so for example, we usually page the lysate, the wash, and then or flow through, so to see if the column is actually working. So yeah, we actually get the pure enzyme.
Oh, all right. Thank you. I didn't realize that you had actually inserted the gene into the plasmid. I just assumed that you had purchased the organism with the gene already present. Okay, so that was nice work. And the other thing about storing the enzyme, do you have it in buffer frozen, or can you freeze dry lyophilize it and actually keep it as solid, or you just use it as soon as you isolate it?
So we aliquot with glycerol, because that helps with preserving it, and then we freeze it at -80. And then because we have the aliquots, it's just to take from there and then to use as we go along.
Okay, and about how long will it last when you have the enzyme and glycerol? Sorry, I'm not talking about, I mean, in theory it will last forever, once it's frozen, but I just mean, do you have to go back to do more fermentations, or usually from one large fermentation you'll get enough to do all your assays?
Right, so from one purification, I do get enough enzymes to do all of my assays. And it does last long. So yeah, it really depends on the volume of work that we're doing, but yeah, it has a long shelf life.
Right, great. Thank you very much.
Okay, thank you. Some non-chemistry questions. What has been your experience like, and how do you think that graduate school in Jamaica prepared you for postdocing in another country? What were your feelings like when you got into the lab and you saw all these other people and that type of a thing? How did that play?
There's a cultural shock or shift as well, because as you would have seen from the work, it's very collaborative here versus in Jamaica, where we kind of have like one specific thing that we're doing. But here it's more like, what's the problem and how we can go about solving the problem. As well as in terms of being in the lab versus, so being here versus being at Jamaica. I didn't know that I was Black. It's only until I came here I realized that I'm a Black man. So yeah, so that's that's a thing, because like you realize that you are in a diverse environment, there are different languages, different ways of doing things. So yeah, it's a good experience, I would say. Yeah.
Okay, so what specifically made you realize that you're black? I mean, and of course we know that you're black, but what were there some specific things? You got specific stares. I don't know what do you mean? Explain
Well,
that a bit.
it's the questions like where you're from, where you're from, what's the ethnicity. So it comes up in conversations quite frequently. And it makes sense because, like, as I said, Canada is a very it's a diverse country versus in Jamaica, where like 98% of the population is black. So we don't go around being like, where you're from and stuff like that. So that's what I mean when I say, okay, I realize that I'm black, because it's a part of the conversation. And yeah, here where different minority groups are at. So yeah, that's also a thing.
Okay. Are there a lot of Latinos in the Canadian space?
Well, in the group we have 2.
Okay.
Yeah, so
What about Asians?
in the group we have 2.
Okay. Okay. And deliberate attempts are made at this diversity?
Yes. So right, we try to be as inclusive as possible, and to give equity, diversity, and inclusion.
Okay. You've cooked any Jamaican meals for your compatriots?
No. Yes, I have. Sorry. Yes.
Okay. Okay. Very well. Very well. Very well. So, having had this experience thus far, what kind of advice would you give to graduate students who are just putting their feelers out there in terms of, so some are about to graduate? What kind of advice would you give them, in terms of, as I said, putting out their feelers to see what is out there and what options they have?
Right. So going about, I would say definitely go for it, because like in a first world lab versus it's more diverse, and there are more opportunities for you to learn and grow as a scientist. How about to going about it? I would say, read broadly and read different researches, and send emails. Just it can simply be like, I read your paper. It was nice. So try and build some type of network, I would say. In terms of my experience, the Mona Symposium was actually a good thing for me, because like it was where I met my now boss, Professor Auclair. And yeah, it started with an email of, just because I was interested in her work, and just showing that interest and asking if there's an opportunity. Then that formed. So from there, I would say, yeah, it starts there. Just reading and being open and sending emails and corresponding.
Okay. Great. Yeah. So what of the future? What's do you see yourself returning to Jamaica? If we had an opening, would you come back home?
I would. We
Wow.
don't have any opening. But yeah, I would.
Okay. That was a recent opening, but so it is. Okay. All right, no problem. Are there any other questions from the students, some of whom I know are of the mindset and modality of thinking, of departing Jamaica to see what's other opportunities could be there for them. Any other questions? Okay. Okay, well, I am not seeing any other questions from anyone. I'm not seeing any hands in the chat. No comments in the chat, no questions. All right, well, I think, Dr. Campbell, that leaves us to just thank you very much for joining us this morning. It is indeed a pleasure to see our graduates go into another space and sometimes succeed and sometimes fail, you know, because the truth of the matter is, I remember when Dr. Genevieve Henry, when she came on, she spoke about the first year and a half being in this other lab where she was doing synthesis, about feeling like a failure, you know, because everything that she did not work. And sometimes in that context, there is that feeling, boy, you know, it's because of my training or whatever, you know. But the truth of the matter is, I'm sure that you've had your share of failures along the road. And, you know, the truth of the matter is, if we're not open to failure, then success is not going to come our way. That is really the essence of it. How have you dealt with failures along this 2-year journey?
Right, for sure. So, as you can see from the work, it is everything that I've not done before. So I'm doing synthesis, I'm working with enzymes, yeah, so it's really trying to use the resources that I have available. So there are times where I may bother people back home who are synthesis based. So that's one strategy. But within the group, we really practice openness, and we really practice trying to help each other. So that's good to foster environment like that. And yeah, it's really, if you don't know something, you just don't know. And if there's somebody within the group that has the expertise, then it's to just to lay out, to talk with them and try and figure out how to go about it. Yeah, and the thing with doing a postdoc is that you're doing new stuff and you're doing it at a fast rate. So, and then you're doing a lot of new stuff as well. So it's gonna be challenging, and you're gonna have days when you're like, all right, it's failing or nothing is working. So like that's a part of the process of doing science.
Yeah.
You just have to wheel and come again. Yeah.
Definitely. Fully understood. All right, guys. So I think that is where we leave it for today. Thank you all for joining us. And as we wrap up, I would like to extend hearty congratulations to Dr. Marvadine Singh Wilmot, who has recently promoted to the rank of senior lecturer. Congratulations to you, Dr. Singh Wilmot. And Dr. Campbell, we wish you all the best as you continue on this journey. And who knows which road it will take you to. But as long as you have that confidence in yourself and that recognition as well that you don't know everything, then you know there is a lot that can be gained from these wonderful experiences all over the world. I think that traveling is absolutely crucial to our lives. And yes, COVID has happened, but let us go there. You know, as you were talking about being Black, I remember being in Spain, I believe, and I saw some Black people in Spain and was staring because they were almost jet black. And I never experienced that before, never seen that before. And so it also caused me to be more understanding with persons who would stare at me. You know, I remember Delisha saying when she was in Europe, I guess when the two of you went to that conference, you know, she was saying how people were staring at her because she was Black, you know, but yeah, the world, ladies and gentlemen, is our oyster. And so my encouragement to all of us is to fly, 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 fly. Thank you very much, Dr. Campbell. Very proud of you and your accomplishments thus far. Keep it moving, keep it going. All right. Thank you all for joining us.
Thank you.